The year is 1955. What could somebody know who's 6 or 7 years old? Okay, a little family history. My uncles, my aunts, my dad, mostly my uncles, I spent most of my time with growing up. They were hot rod builders, auto mechanics. So here I am, I'm a little guy, and I'm being watched by these guys, right, who are taking batteries out of cars, starters, generators. But right from that age, that was my interest, was how do I take this DC motor, which at the time was 6 volts, and connect that DC motor to the generator that's laying over there that's also 6 volts. So I just put gen motor. Pretty simple idea, isn't it? Every kid does this. Well, if they're into this. Most go to prison now. All right. So, the little kid figures out a way with a piece of rubber hose, right, to put these two together. And he puts a storage battery down here. So can you all see that? Okay. And he says to himself, all as I must do is go like this. That's pretty good, isn't it? And the thing takes off when you hook it to the storage battery, and all of a sudden, this starts going slower and slower and slower, and the generator isn't putting anything out, right? So the little kid says, yeah, but when I take these wires off here, and I take this and I put it down here to a light bulb, right? To this light bulb, it lights up. And it keeps lighting up. And you say to yourself, well, wait a minute. I don't like that. So again, you attempt the same thing. And it starts out fine. And then all of a sudden, it goes dead. There's no more coming out of this, and the motor is just spinning away at whatever level. And you say to yourself, that doesn't work, but that doesn't stop you. You start trying to conceive of all different kinds of things. So, if you're intuitive, the next thing you try is you put a light bulb in here. It's lighting the light and a little bit's going back. But this is going down like that at this rate. in time. So you think you got something here because it's taking a while for this to go down. And so you take it to school, which I did, and you demonstrate it for the classroom. And the science teacher, who's really educated, right, says, that'll never work. Yeah, it's lighting the light bulb right now, but it's not going to light it forever. There is no perpetual motion. John. So why don't you just take that and don't disrupt the class anymore? Because it's much more important to mix the baking soda with the vinegar. And shoot it out the end of a straw, because see, you're going to be a rocket scientist one day. And people love rocket scientists because that's exactly where science is. You know, and then the next little thing in the class is, John, don't ask how you can get electricity out of that. Yeah, but there must be some way to get electricity out of baking soda and vinegar. I mean, it builds up pressure, doesn't it? And that can fire a turbine, and that turbine can turn this generator, right? And obviously it could, but not at 6th grade. Okay, so this is where John starts, and this is exactly what John did. However, John was not the type to give up. And I said next to myself, there's got to be a way to do this. To take this DC motor and to hook it to this generator and make this keep going, make it keep running. Well, we all know that, and I've said this many times, the term free energy is a misconception. It's a term that shouldn't be used, because this energy going in is one form of energy from the chemical in the battery. And the energy that's coming out over here is another form of energy, and it's totally different. Unless you put it to something that will charge and put it back in the chemical. So, is it really free energy? Or is the energy already there and these things are just utilizing them when you rotate them? I think we're all surrounded by all this energy. We just haven't found a way to couple it, get it out. So John takes this further. John decides, let me do this. John decides to put a push button here. And then take this back over here. Interesting, isn't it? Because this is, when you're at that age, everything works in your mind. You can make no mistakes. You are a fearless person. Right? So, John notices his uncle gives up 2 amp meters. Well, actually, the uncle didn't give them up. I just borrowed them. So I noticed you push this button, and this one goes up, and if you let the button go at the right time, that one goes up, and that one goes down. So, where does everybody think I'm going here? Right? But 7 years old or 6 years old with a hacksaw, how straight could the cut be that you're cutting, right? So John sits and thinks for 2 or 3 days, and he's going to school and he's discussing this with people that don't know anything, less than John knows. But I have a friend in school. I don't go much into this story in the DVD because I get right to the point. So if you can't remember what I'm saying here, there are DVDs available on this presentation. Anyway, the friend and I, we take the motor apart. We notice that the motor has what they call the commutator in it. And that each time the brush makes connection on each side, the motor goes. And so I sit there for days of just taking the DC motor and pushing the switch and making the motor go as it's bouncing around this way, right? But like I said, a kid's fearless. He doesn't know. He'll just touch the 2 wires to the battery together and they'll be, hey, look. Which somewhere I do have the scars. But anyway, so my concept at that point is to take the commutator to try to make one. And I say to myself, okay, if I'm able to make this, right? And at first I tried tinfoil, and tinfoil doesn't work. And then I tried copper sheets. But of course the glue that I had didn't hold it on, right? And so finally, what I said to myself was, why don't I just rip apart another motor, take the commutator, because it fits that shaft. Put that commutator in there. Now I'm not changing my concept, you notice that. I'm still staying with the DC motor, and I'm still staying with the DC generator. Because generators at that time, if you got them going at the right speed, they self-excited, and they just put out electricity. They're like magnetized. So anyway, I decided to take the commutator, and there's all these segments in the commutator. And I just decided to split it. Take all the wires off and make all this just one switch. But then I said to myself, wait a minute. How do I get to that switch? So I wasn't thinking. I decided that I needed 2. I needed 2. For the simple reason is I needed to have it switch, and I needed to have this portion go out to some place that a brush could touch. So I do all that, I put it all together, and basically it looks something like this, with the two brushes here, and the switch. There was a brush here and a brush here. And I actually got this. Okay, I had the input wires, and then the wire could go over here, and this wire could go up to this one. Then this is actually the switch. I'm going to tie something in here for you for a second. The Lockridge device. So now, I got all this together, and I'm not actually drawing this correct, but you guys get the idea, right? And it's phenomenal, because now it runs. It arcs a lot, but it runs. Brilliant blue arcs coming off trying to file down brushes. So, I still don't know anything, but I'm willing to learn. So what I did was I ran the motor as a direct motor first. I charged the automobile battery at I had a Western Auto 1 amp battery charger. With a 6-volt automobile battery that used to be this big, you're not going to put a charge in it in 20 minutes or 10 minutes. You're going to wait all night. And if you're lucky, the next day it's done. So I waited 18 hours to charge the battery. And then I ran the motor straight without the switch. And I made curves of how long the motor would run before the battery. And when I say battery was zero, I mean zero. Because batteries made back then could go to zero without harm. Because anybody that grew up in those years used to be able to go out in their front yard, and when the car wouldn't start, just crank, 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 crank with a starter, and then it would die, and you go back in the house, have a cup of coffee or whatever you were doing, and come back out and crank it and then start. So it was a totally different battery than what is manufactured for us today. He's shaking his head, yes.
I didn't know that till you said it, but I can see that it would be the case.
Right, because the pasting method was different. The mixtures were different. The EPA wasn't here. There was no environmental problem that we knew of. Hell, people used to take their engine oil and dig a hole in their yard and dump it. My idea of that was, watching this was, oh, no problem, because one day you just put an oil well there and you have gasoline again. Well, I mean, that's the way kids think, right? It's an imaginary world, and the whole machine is imaginary. And you really don't know what you're doing, and you don't know nothing. So then I ran this curve, and I got the time when it started to fall of like an hour and 15 minutes or something, whatever. And then when I ran it with the switch, being pulsed, I got a completely different curve that looked like that. And it ran that much longer. Now everybody knows why it ran longer, right? Because it was pulsed. Wasn't always on. Battery could recover a little bit in between these faulty contacts. However, when that occurs, something occurs in the switch where it's arcing, and somehow that's an energy of some kind that mysteriously somehow gets back here. Reverse each time. So it runs a little bit longer. Later on, now a year goes by, and I'm still daydreaming about this machine that I want to make. And I decide, I'm playing with an old tube radio one day. If anybody, and people know what those are. They had little inverters, right? And I always used to take the inverter out of the tube radio because it had that power supply that would knock the hell out of you. It would buzz away with its little inverter. And of course, like all kids do, they discovered that you could charge these canned capacitors and hand it to your friend. Of course, you get beat, and he gets the biggest jolt of his life. So I'm watching that, and I said, let's just take the generator and charge up the capacitor and see how much voltage we get. Well, of course, charging the capacitor is relatively simple if it's 40 microfarads or 80 microfarads in those days with the generator. And of course, the generator, you know, has to put out double the voltage to charge the battery. So it's unloaded, it's not going back to the battery. And this thing here is about 10.5 volts. And when you short it out with a screwdriver, it almost melts the end of the screwdriver. So you show your friends until you get burned, or until it melts the tip of the screwdriver off and that flies and hits you. Come on, man, we're only little kids. We can fly, we can climb. Umbrellas work on roofs. You can jump off the roof. Mary Poppins did. So what I found out, by then, kids don't want to play with you anymore. We don't want to go over to this guy's house. He does some weird stuff. I mean, he's got storage batteries, and he's got lights running, and he's got this doing that, and his mother gets really mad because his clothes are full of holes, and you know, he's got a pipe with gasoline in it in the garage with a spark plug mounted in it. So. You're just more, is it in you? You see what I'm saying? Is it in you to do this? To really understand what it is? Because nobody does. Anyway, so we just decide. Of course, you go to your dad in the meantime, but see, your dad my dad worked on the space project early on, actually working on the nose cones for the first astronauts to go to the moon. And I used to say to Dad, Dad, can you bring me home a light bulb? Well, what'd you do with the one I gave you? Burned it out. How'd you burn it out? Hooked 2 batteries up to it and it went pop. You're not supposed to do that, John. So he would sneak me home a light bulb. And then I'd have a new light bulb. And then, back then at Lockheed and places like that, and Rocketdyne and stuff like that, all the engineers were sort of loose with their parts. If you'd walk down the street and somebody had a hobby, right, and he was a ham radio operator or something, you might be able to finagle something out of him. But he'd just give it to you and laugh because you were just a kid and you weren't going to do anything with it, okay? So this is what I tried. Now this is at 10 volts. This is dropping. The motor's running. The generator's putting out. And you push the switch. But you don't push it too long, because then this slows down. And then this is what I noticed. A very slight effect. Not much of an effect. Had an analog voltmeter on this one and an analog voltmeter on this one, so I could see one charging, one discharging. But what I noticed was that this would jump if it was in between where this wasn't making contact. Well, later on in years, my friend Norm Sides meets people that knew of a machine that worked like this that came out of Germany, called the Lockridge device. Except the Lockridge device had a much bigger capacitor wrapped around it, and it fed back through the switching mechanism in the motor, and the motor ran itself at 5,000 RPMs and gave you 300 watts. Well, that's pretty good for free energy, isn't it? Except for one thing. It was only free for a little while because the brushes would wear out. And when you went to put brushes back in the machine, you didn't know that Lockridge had filed the brushes the same space as the commutator segment, so the machine wouldn't work. And the people would throw it out. They would scrap it for the copper in it. And that was probably pretty good at that time. Anyway, this is where I discovered this. And I don't do anything with it for years. I go and I do my cars, or I do this, or I do that. Girls were more important then. Yeah. So, that's a little basic history of where the story starts. The SG machine. Later on, I go into the military, and I take the MOS, 31M MOS, and I decide that I want to do microwave engineering. Nice subject to start with, right? Since you know nothing but that, but you've had this tinkering interest all this time. And so the military trains me. And you learn the basics. And then you get assigned and you go somewhere and you do something. And you discover something else. But in the meantime, you're thinking about all this. And about other things. But the point is, you got a basic understanding, you got a basic knowledge, you got a basic things with Ohm's law and frequency and the whole bit. So later on, this is now jumping to probably 1970. I'm sitting in the garage one day, and I'm saying to myself, God, you know, I really would like to do that. I'd like that to work. Well, now you're a little bit bigger. You don't have to worry about the hacksaw blade because you can push it. And you can follow a straight line because you learned to mark a line instead of just guessing, right? Of course, 71, 72 comes. I meet my wife back there, Rhonda, and I forget about all this. And so I think one day, Rhonda came into the shop, and she sees all these little Tinker toys running. Little pulse motors. But no contacts. Because, see, you learned. You learned what the transistor was. So you learned to take that device and with another coil you learned to switch it on when the magnet went past. So later on in years I built a model of that. But I just didn't want a pendulum. And as you can see, without hiding it, there's a battery under it. And a circuit that's just tweaked together. It's not even soldered. Okay, so you learn that pulse motors, let's get this to do its thing, can do this. But you're not capturing any energy there. You're expending it. Although it's generating an energy, nobody's taking it. So anyway, you watch those for days and days, and they're clicking away, and this is doing, and you make a bigger one on a particle board and say, oh, geez, if this works, right? If this works, I can put it on a wooden box, and instead of using little magnets to find out, all you got is 4x8 blocks that are 6 inches long and 1 inch thick because you were doing some other experiment. And you leave it running in the middle of the night, and the hot glue comes off and the magnets are in the ceiling. Because it speeds up and it's gone. But you're not taking any energy from it. You're not doing anything with it. So you go through this and you do this for a little while and you watch how all these motors run like this, you know, but you don't take any energy from it. You're just running it as a motor, and it's not really even a motor. It's not good as a motor. And you find out, because I think at that time we had the new magnet, which was samarium cobalt. And you find out that samarium cobalt, you know, when you have this coil and the iron and everything, doesn't run too well compared to the ferrite. So, the SG. How did the SG come about? Does anybody know? No. No. Stand up, Gene. This is how the SG came about, known as the schoolgirl motor. No, I'm going to tell. I just wanted you to stand up. So, she wrote the article. little girl came to me one day. She wanted to do a science fair. And she said, I want to make this motor. And so the motor that she was supposed to make was the motor that's in this book, which is you wrap the copper wire around a couple nails, you put tape around the nails that you tape that to, and you just run the crap out of the battery, and it dies. So I looked at her for a minute, and I really didn't want to say anything. But I knew her dad, and her name was Shawnee, and I said, Shawnee, I can't do it for you. You're going to have to do it. But here's how you do it. I know that she can't cut out any plastic circles because there's no way she can do it. She's probably worse with a hacksaw than I was. So I was building something and I had all these plastic circles and I gave her the plastic circles. Take this magnet that's a bar magnet and hang it from a string. And she's looking at me kind of funny, right? But there's something basic here that I wanted her to learn. I said, hang this from the string and don't touch it. I said, and then whatever pulls facing north, mark the magnet. Oh, I could have handed her, a compass and said, do that, right? But I wanted her to learn about a compass right there. So she does it, and I say, okay, now mark all the poles, and I want one pole here, I want one pole here, and one pole here, and I'm sort of giving her a drawing, but I'm not doing the work. I'm making her do the work. So she figures out that she can't attach these on the outside of the plastic. So she is clever. She puts them on the inside of the plastic so that the perimeter of the wheel is unaffected by the magnets on the outside. So I looked at her for a minute and she's got those glued on there. Of course, giving her little tips all along, but we're not allowed to touch it. We're not allowed to do this. She has to do it. And then she also has to write about it. So I said to her, I said, Shawnee, how are you going to get the two-wheel center? You've glued one side, and now you got to glue the other side, right? How are you going to get the wheel center? Just because there's holes here, that still doesn't mean that you're not going to walk one off. And the shaft's going to be like this. She says, oh. She says, I'll cut out a piece of styrofoam. And I'll push it down in the styrofoam. And then I'll glue the top magnets and I'll push that down in the styrofoam. How about it? Well, as it turned out to be pretty close to center. So she figured that out. And then she said, but wait a minute, how's this going to run? There's no, according to my little science book here, there's no commutator. I said, well, you're going to make a transistor circuit. You're going to make this, and I tried to do it. I want to draw the symbols. She wants pictures. So I said, this is the transistor. And of course the numbers are up here and blah, 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 blah. And I said, this is B, and this is E, and this is C on that particular transistor. And so I drew this pictorial of that this has to go to a coil, right? And I had to give her that that's a bobbin that you wrap wire around. And you cut these pieces of metal and you put them in as a core. So I had to do that. And then I said, but you have to wind two at once. So she ends up with two coils. They don't look very good, but they work. And I said, you know, the one side of the coil goes to the battery plus, and whatever side that trigger wire is on, right, that's the positive, and you need a resistor to the base. But I had to draw a picture. And I said that has to be 35 ohms for what she was doing. And I said, you need a diode in there, so I had to show her exactly what a diode was, and she did this. And I said, the other one goes to the other side of the battery. And it sort of was fun to watch her face when she did all that, and she put it on this little board, right, Gene? She had it on this little board. And she gave it a spin, and the thing took off. And it probably did 2,000 RPMs or better. And so she's not the kind of kid that said, I'm absolutely satisfied with this. No, not her. She decides it's a generator. So she bends a coat hanger, if I remember right. Is that right, Gene? She bent a coat hanger.
Your father helped.
Yeah, her father helped her do that. And they put a coil up here, and then they hooked that to an LED. And it worked. Anyway, she takes it to school. And the science teachers look at her and say, you can't participate. Why? Well, there's no commutator. So, if I remember correctly, what happened was all the kids in the class went in an uproar immediately. I guess their social engineering didn't work right there. So they all went in an uproar and said, no, 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 no. Shawnee's in the science fair. Well, she won all 3 awards. And that's what Gene Manning wrote about. And we called it the schoolgirl motor. And that's what the schoolgirl motor was. Only with a generator on it, up here. And that was plastered all over Keeley Net and blah, 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 blah. So I took it a little further in the history here on Keeley Net. Actually got into several fights on Keeley Net about this. I think there was a guy by the name of Elick booted off because of me. But I said, make the motor the way that they made her motor, and make this motor charge a capacitor with a timing belt and some contacts that went up this way, right? And I said, don't charge the front battery. Charge a second battery. Because nobody cares about the primary energy. You shouldn't care. You want it, you don't care. Because this energy is different than the energy that's over here. It's isolated. It's not one and the same. So this basically is its own loop. This basically is its other own loop. So I ran this by KeelyNet, and several people built it. Of course, not too many could even find an MPS 8099. You know, they said, well, that doesn't exist no more, John. That amplifier transistor's gone a long time ago. Wrong. It's never been gone. You just got to know where to look. So anyway, the plans were up there on KeelyNet. They're up there to this day on this. And I decided, actually, at that time, we decided when it was changing over from Bedini Electronics to BTI, we decided to file a patent on it. So we did. And that became the monopole motor, because we only termed it the monopole motor because it only used the north poles. But the patent states, nowhere in the patent do you see the word what? What does the patent say? And I know you've read it. Is there really such a thing? What actually is back EMF? Does anybody know? And what's its level compared to the battery that's driving it? I wrote a paper of which I sent off to the University of Edinburgh with Dave Clemens, who was a PhD in mathematics. And the electrical engineers, I said to them on the phone, I said, you have this battery voltage, right, from 0 to here, and you switch, right, but the back EMF is always less than what the real input voltage is. So wait a minute, is back EMF charging this? Hell no, it can't. But what can charge it is, as Frank said last night, you have Lenz's law. Bang! Well, where's the back EMF? Now, there are three basic things and I'm sort of going to go through these one at a time. Isn't this the basic SG circuit? That's it. Right? Of course, the rotor's out here, isn't it? And you bifilar wind this, right? So this is your basic SG circuit, right? Well, there are three modes of operation to this. So far, what I've seen out there is everybody only has one mode. Where's the other three? Or the other two? In this mode, you can only capture the spike. So, what are you missing about what the energy is? Does anybody know? It's very short, right? And it would take an awful lot of these to charge that battery over a certain period of time, wouldn't it? But that's the way it's designed. This is exactly the way it's designed. It's made to take what everybody wants to term as radiant energy and charge that battery without any current. Now, you know, if the spike looked like this, there'd be an awful lot of current there. Enough to burn down the building probably. But that's not what's coming out of the machine. No. Not yet. Don't jump ahead of John. All right? What's coming out of the machine is this spike with very short time. And only this. From there to there. And everybody says, oh, it's a 300 volt spike. No, it's not. Subtract the battery. So what is the spike? You've just lost that. Right? And everybody said, well, that's the back EMF. No, it's not. That's not where the back EMF is. So, for this to generate, for this machine to generate current with that type spike is impossible. Well, yeah, but it charges the back battery. Yes, it does. But why does it charge the back battery? Answer if you know.
Provides acceleration to the ion.
Exactly, Frank. It piles up on them. It piles up on them for free. Oh, free. The ion's about that big. And if there really is an electron, it's only about that big. So, it accelerates these particles through what?
And their mass.
Yes, but you're more knowledgeable. So what actually happens here is the lead plates are sitting here and here, and they want to be charged, but they're not charged. So when the machine comes along and the spike, so you notice it's in positive direction on the positive end of the battery, and this going back to the positive up here. But that could be totally wrong, which you shall find out. Anyway, it keeps piling these up. And that guy goes that way. Under his own speed. You cannot force nature to go faster than nature wants to go. Otherwise, terrible things happen to you. There's probably a better way to explain this. There's 3 kids. And there's a ball. Each one's got a ball. One kid sprays water at the ball and it goes. And one kid throws something at the ball and it goes. And the other kid says, well, wait a minute. And he kicks the ball. And it takes off and goes. And then he turns around and kicks it again and it takes off and goes. So, without taking the SG circuit off there, and expanding the plates out this way. The ions here the spike comes along at this level because this is going downward. This level. And kicks that ion here. Next spike comes along, kicks the ion here. Next spike kicks the ion here. Next spike kicks the ion here. Next spike kicks the ion here. So all these little kicks are constant, like this, from this machine. So, if you add them all together at the end, current-wise, there's this much current in this one, this much current in this one, this much current in this one. So it's a pretty steady stream because this is actually rotating at whatever speed it's going to go. But look at all the little kicks as it goes around, right? So, of course it takes, under this condition, it takes hours to charge. All right? But this is only one basic function of the SG. There are 2 more that people, I don't know why they haven't discovered it, why they haven't seen it. Okay. The next way is to take all these spikes, transform them, and charge a capacitor. But we're not talking about 50 microfarads here. We're not talking about 1,000 microfarads here. We're talking about what you see right here, 30,000. And we're talking about taking the 30,000 microfarads and only allowing it to charge to like 24 to 30 volts and no more. Now, if the battery's at 12.6 and the capacitor is at 30 volts, how much voltage is in the capacitor when it dumps? Right, Frank. Right, about 15 volts. So, where does the battery want to charge to? About 15 volts. So the next problem is, I just can't take this and just put it back to the battery without doing something to cause it to charge up, discharge, charge up, discharge, charge up, discharge. So, you have to be clever about this because it really doesn't make any difference what this is doing out here because it's pulsed. It's in its own loop. Now it's got a secondary loop. All right? But the ideal situation is that you would charge this capacitor here, right? And on your secondary battery, you'd want to hit the negative pole. So you would take this and this, of course, would go to your FET. All right? Between there and ground. I drew that wrong, but kind of hard to do it here. So the gate would have to be fired by something. You wouldn't want to use a transistor because the voltage drop on the transistor would be a little bit more than you'd want. So you'd lose a lot. So you would take the FET and you would actually switch the FET. Is actually going to look like this. So when this got to exactly whatever voltage you determined, that the comparator said, turn on the FET and dump this charge. Now, if you were looking at this capacitor with a scope, what would you see? Does anybody know? Right. That's exactly what you'd see it generating, is a sawtooth. Charge, discharge, charge, discharge, charge, discharge, charge, discharge. There's a little more complication to this because you can't burn or use up very much energy in the comparator. So you can't do it. You have to do it with something that's going to take very little energy to do the switching. And of course, everybody knows what a comparator is. It's an op amplifier, basically, right? Forget about the Radio Shack one that turns on LEDs and everything because you need something a little bit different. It's something that has a reference voltage that's locked, like 5 volts. That pin is locked to the reference. And that's done by a regulator. And that regulator, of course, is tied to the capacitor. So now, since the op amp, right, this also is very important, the op amp, because most op amps are going to give you a little bit of difficulty if this goes higher. You're going to burn it up. So you have to have another regulator. Regulators take energy to regulate that. So see where I'm going? So now you have this energy and this energy. However, now you have to have a divider, and you have to be able to adjust that divider. So whatever these are, you know, you would want to be able to tell the comparator to either go up in voltage or down in voltage, and then stay at a certain portion. But however, you're going to have to watch this, because as the battery rises, the comparator will change speed until it's on. Period. At which time the SG has a filter capacitor across it, and it's not dumping anything. But the battery is maintaining that voltage. And you don't want that. You want this so that you can select it so it stays in a certain range, and it's a window, all right? It's not real critical. It's not here. It's not here. You just want it to stay in this window until the battery gets to where you want it to charge. And you're done. When the comparator comes on green that you're measuring it with, you're done. Well, John, that's only a surface charge. No. If your battery's any good, it's done. Don't sit there with it and try to make the battery go up and up and up and up, because you could push the battery to 16 to 17 volts, and we will do that so you can see it. But we're not going to do it in this mode. This is the second mode of operation. Now, one more important thing is some comparators like to switch up and have real difficulty switching down. So, does anybody know the term for that? What you have to do to correct it? Exactly, Frank. You have to put a loop around it. That's why everybody that second-guessed John trying to make the comparator didn't have the hysteresis loop. So therefore, the comparator really doesn't operate correctly. And what was the complaint on the internet? The front battery is running down and it didn't get the back battery charged. Really? You have to take into consideration all these things. You have to methodically go through every portion of the circuit until it operates the way you want it to operate. You just can't take the circuit off the internet that somebody put up there, because you're just copying. And his mistake is your mistake. In fact, you made two mistakes. You not only copied the mistake, your judgment said it was right, and you made another mistake. Okay, mistake. I'm going to put an M here, so I'm going to come back to the mistake.